This is a servo, and it can do amazing things like this, and this, and whatever that is, and this, but it has one big downside. Can you guess what it is? If you didn't get it, it is the noise. It's a boring, obnoxious sound. Now you might think that's not very bad, but picture yourself in a factory with hundreds, maybe thousands of servo motors and other motors making different types of noises. If you picture this, you can understand why people wear hearing protection when working with machinery. This video is my attempt to try to make a servo motor a little funner to listen to and possibly give the machine a bit of personality outside of what you normally expect by having the motor itself play music or a beat or something while the machine is running. To do this, I need a way to make the motor act like a speaker without messing with the functionality of the machine. On some machines, this is extremely difficult, but on others, it just might work. It is not something you would do to just any machine, but I will say the thought of walking into a factory and having a machine that sings Whistle While You Work or something else might bring a smile to my face. Before we can try to make a motor act like a speaker, we really need to understand how a speaker works. In today's video, it's going to be broken down into 4 parts. The first part is how a speaker works. The second part is the math needed to make a wave file. The third part is how I'm going to demo it. And the fourth part, we're actually going to listen to the servo motors play Beethoven. In today's market, there are many different kinds of speakers. Some are small, some are big, some have different colors. But the majority of the speakers all work the same. To understand how they work, let's look inside of a speaker. As you can see, as this speaker expands, there are many parts to a speaker. But most of these parts of the speaker are not important. So let's only show the parts that are important. You can see that there is a coil, a magnet, and a cone. The magnet and the coil are the key part of the speaker, and they produce the sound when an electrical circuit is hooked up to it. In this demonstration, I'm going to use a sine wave. A sine wave is the simplest form of a wave. Here you can see there are 3 sine waves, and we're going to show how the speaker behaves with each of these sine waves. Here you can see that I have a little green bar that's connected to the coil and this sound wave. The purpose of this illustration is just to show how the speaker behaves as the wave moves. Here you can see the wave is going back and forth, and the speaker is also going back and forth. Alright, let's compare that with a different waveform. You can see from this waveform that it is faster. This makes the pitch higher. Now if we compare it with this waveform, you can see that the wave is not as tall. This is the amplitude. The amplitude is smaller, and so the sound will be softer. You can see that the wavelength, or the speed of the wave, is the same. So the green wave and the blue wave have the same pitch. Now let's look at the equations. Here you can see an illustration of a sine wave. The gray line that goes from left to right represents the value of 0. The copper-colored wave is the sine wave. In the top right corner, you can see the word amplitude. The amplitude is used to adjust the loudness of the sound. In the top left, you can see the word period. The period of a wave is used to adjust the frequency of the sound or the note. The period is measured in the units of time. At the bottom, you can see the equation for the period. The period is simply 1 over the frequency. So as long as you know the frequency of each note that you're playing, you can simply plug it into this equation and find out the period of that note. This is pretty handy. Here you can see the period for the note A is roughly 2.2 milliseconds. Now, because we are trying to produce a sine wave, we are going to use the sine function. Here you can see my equation is the output is equal to A, which is the amplitude, times the sine function. Inside the sine function, you can see that I have tau times the change in time divided by P, which is the period. A, of course, is used to adjust the amplitude, and this is because the sine function is always between 0 and 1. So if you want to make it twice as loud, you would put a value of 2, which would make the amplitude on the output between 0 and 2. Now let's put our note A into this equation. The note A has a period of roughly 2.2 milliseconds. So if we put it in our sine equation, we will have A times the sine function times tau times the change in time divided by 2.2 milliseconds. Now that we know how the math works so that we can code our drive, we still need to demo this somehow. My thought is I'm going to make a clock, but instead of numbers, I'm going to have each of the notes on it. And as the music plays, I'm going to have the arrow point to the different notes. If you look at my faceplate that I just made, you can see that the letters are not evenly spaced. This will make my demonstration of the arrow pointing to the different notes look a little off, but that's because I was being lazy and not actually have anything to do with the functionality of the code. You can see if you look closely, the letter E is actually shifted quite a bit down, and so it messes up with everything else. So just forgive me there. This should also beg the question, how am I supposed to do two things at the same time? If you look at this motor on the left side, you can see that I have a demonstration of me pointing to different notes. This represents the motor actually doing a job, kind of like what you would find in a true system. And the motor on the right side is acting like a speaker. Well, how am I supposed to do both at the same time? Well, in the servo world, we call these profiles, and certain servo controllers can't do more than one profile at the time. Others don't allow you to add custom profiles to a profile. And so you need to be particular in the servo controller you pick in order to be able to do what we're going to do today. Now, the servo controller I'm using today is the M700. It allows me to use the onboard profile that's built into it and add it to a custom profile. Some other servo controllers will allow you to do what we're doing, but you have to write everything from scratch. With this one, we only have to write the music portion in Codesys. So we're going to put the Codesys in the MCI 210 module, and we're going to have it sum the onboard profile to the music profile and output it to the motor. I'm not going to show you how to do that today, but I will in a future video. As far as today is concerned, I just want to tell you a couple extra things. First, it is possible to actually have your motor play more than one note at the same time. In fact, I made my motor play up to 4 notes at the same time without any problems. Unfortunately, a motor can't point to 4 different notes at the same time. So instead, I have chose to use 4 motors, each pointing to a different note. Over on the right side, you'll see that there are 4 motors. Each of the 4 motors will be playing a different part of the music. The top left will be playing the first part and will be heard primarily in the left speaker. The top right motor will be primarily heard in the right speaker and will be playing the second part. The bottom 2 motors will be playing different parts as well, but they will be heard in both speakers evenly. On the left side, you will see the music scroll up as the motors play the music. Now, the music on the left side is technically from when I was having a single motor play all 4 parts, but you can see what's going on with each of the motors. Now, without waiting any longer, let's play Beethoven's 5th Symphony. Hey, welcome to the end of the video. If you liked it, please subscribe, watch another one, put some comments down below of things you would like us to make, or whatever. See you next time.